The focus of this lesson is going to be quadratic inequalities. So we're still going to be looking at quadratics, but rather than being equations with an equal sign in between them, we're going to be looking at inequalities. So the comparison there might not say that it's equal to 0 or equal to a number. It might say it's less than or greater than or less than or equal to or greater than or equal to. So let's think about the differences that would happen here as we look at each of these things. So in the first equation here, we're going to do part A. We're not going to do part B. However, we'll talk about some comparisons between them and what we would expect to see. So in part A here, we have a quadratic. I can tell because it's x squared. But notice that rather than y equals, exactly like we just mentioned, it says y is less than or equal to the equation. So we're going to remember with inequalities, you guys have done inequalities with lines, and that the line was a boundary, and all the points that were solutions were shaded on the graph on one side of your boundary. So the difference here is that our boundary is no longer a line. This boundary is going to be a quadratic. So we're going to go ahead and graph this quadratic. So in standard form, we like to start with x equals negative b over 2a. And so when I simplify that, I'm going to get negative 3. So negative 3, or the line x equals negative 3, is my axis of symmetry. My vertex will also lie on this line, which means my vertex is the point negative 3 comma something. I'm going to figure out that y coordinate by plugging negative 3 into the equation just as I would if it were an equal sign. Because remember, we're graphing first just like it's an equal sign, just trying to get the outline of what this parabola looks like that's going to be our boundary. So we're going to go ahead and simplify this, and we're going to get 11. So the point negative 3, 11 is the vertex of this parabola. That's 1 point higher than I have marked on my graph, so I'll just go ahead and mark it up there. And then in order to finish graphing the parabola, we need some points on the side. I'm going to go ahead and plug in 0. When I plug 0 into the equation, I'm going to get 2. So I know I have the point 0, 2, and then I should also have its mirror image on the other side. So these are points that are going to create the parabola. I'm going to draw in the boundary, and now I need to pay attention to the inequality. When I look at the inequality, is y allowed to be equal to this quadratic negative x squared minus 6x plus 2? Because the inequality says it can be less than or equal to, it can be equal to the boundary, which means I'm going to draw a solid boundary rather than a dashed boundary. Okay? So a solid boundary. Now, my graph has been split into two areas. Okay? There is this area. I'll try and show you here and then erase it. There is this area that is all beyond the parabola. And then there is this other area that is all inside the parabola. Okay? Those are the two areas that your graph has essentially been split into. We have to decide which one of those areas represents the solutions to this inequality. Where is it that y is less than or equal to all the points along this boundary? And I erased one of them. Sorry. Fix it. So I'm going to go ahead and plug in a point. Okay. So I'm going to plug in a point that is not on the boundary, but is clearly either within or outside the boundary, so I can test if the solutions lie in that area. I'm going to choose that is not on my boundary, so that's why it's my choice. And I'm going to get this statement. 0 is less than or equal to 2. This is true, which means 0, 0 is part of the solution set. That means this point right here, 0, 0, should be something that is shaded and is included in our solution set. So I'm going to go ahead and shade everything that's in that same region as 0, 0. If the point had been false, I would know to shade the other area outside of that boundary. Okay? So here is a representation of y is less than or equal to negative 6x squared minus, or excuse me, negative x squared minus 6x plus 2. We're not going to do part B, but if you take a look at part B, notice one main difference is that the boundary would be dashed and not solid because the inequality does not have an equal to included in the sign. Okay? All right, so moving on. We're going to use our calculator to look at what some of these would look at like and just show you guys a couple things. So we're going to look at part A again here. Notice it says 0 because we're actually going to solve, which is a little different than graphing. We can use our calculator to solve if we think of the 0 as a y. Just like when you are solving quadratics with the quadratic formula or by factoring, you go ahead and you have something with y in it, and when you go to solve, you make y equal to 0. So we're going to put it back as y for the moment so that we can type it into our calculator and look at what that's going to look like. So on our calculators, I'm going to go to y equals. I'm going to clear out whatever's in there. I'm going to turn off any plots that are graphed. And I'm going to type in my equation, which is negative 3x squared plus 5x plus 2. Then before I go to the graph, because the fact that my plot was on and stuff like this, my window's probably crazy, I'm going to go to zoom and I'm going to choose standard and see if I can see the parabola in the standard window. Okay, and I can. There it is. All right. Now, I didn't do something correct. There's no shading on this graph. Okay. So what I'm going to do is go back to my y equals and show you something we haven't seen before. If you arrow all the way over past the y equals, notice that my cursor is right here. Okay. And if I press enter on there, it's going to change what that looks like. Okay. And notice that my equation said y was greater than, which means y is above the parabola or more than. So I want to press enter until I see the image that has shading above a boundary. So here's a picture. That's just a darker line. Here's a picture where shading is above the boundary. Okay, so that's what I'm going to go ahead and choose. Now I'm going to go back to my graph. And now we not only see the boundary, but we see exactly what the shading looks like. If we're trying to solve this problem, if we look back at the problem, we were trying to solve, it was set equal to 0. Okay? So if I set it equal to 0, those would be the intercepts. So I would want to know what those x-intercepts are, and then we'll talk about how to know where the x values are, where it met the inequality, and not just the equal to part. But looking back at our graph to find the x-intercepts, remember how we do this. We go second, trace, or calculate. We want to calculate a 0, so choice 2. And then you want to take your cursor close to the 0 that you want to calculate. You want to go below, press enter. That's our left bound. Then we want to go to the right and press enter for our right bound and guess. And one of our zeros is negative 0.3 repeated. And so I'm going to go ahead and record that. 1 0 is negative 0.3. The other 0, the other place that it crossed the x-axis, I need to calculate that as well, so I'm going to go through the same actions. I'm going to scroll over to the other side. Something to the left will be my left bound. Something to the right will be my right bound. I will press enter, and 2 is my other 0. So I have 2. So if we were solving an equation, these would be the solutions to the equation, but we weren't. We were solving this inequality when 0 was greater than or equal to negative 3x squared plus 5x plus 2. Okay? So think about what you saw on the x-axis. you basically saw the parabola crossing the x-axis at negative 0.3 and then again at positive 2. Okay? It went something like this. And then all the shading was all around the parabola. Okay? Notice the parts of the x-axis that got shaded. All the x's from 2 over and all the x's from negative 3 over were the x values where the graph was shaded. So our solution to this original problem that has an inequality instead of an equal sign is to say, where did the shading occur with respect to the x-axis? So when I look at this picture, I want to say it occurred here and it occurred here. And the way I say that with inequalities is I say that x was less than or equal to negative 0.3 or x was greater than or equal to 2. Okay? And so that would be my solution for this case in this inequality. But I really couldn't see that until I saw the shading. Okay? So let's talk about how to do this without having to put everything into the calculator and how we could analyze it if we were just looking at a factorable equation. If it wasn't factorable, you would just have to find the solutions using like the quadratic formula or something like that. So if we look at example 3, part A, it's already factored for us. Okay? So we know that on the x-axis of the graph, it's going to cross where the solutions are. So think about if you were trying to solve x minus 4 times x plus 7 equals 0, you would find a 0 at x equals 4, and you would find a 0 at x equals negative 7. And so we would have at negative 7 and at positive 4 the places where the graph is going to cross through the x-axis. Okay? Now, in my inequality, it doesn't say equal to here. It says less than. And because it says less than without an equal to, the boundary would be dashed, meaning it hits at these points, but we're not allowed to include them in our solution. So I'm going to mark them open. Okay. Then there's two ways for me to analyze this. One way is to think about how the graph would be sketched. If you were sketching this graph, it would start with x squared. It would be a concave up parabola. So your graph would be looking something like this. Okay? And think about what the question is asking. It is asking you, when is the parabola x minus 4 times x plus 7 less than 0? When does this turn out to be negative? Okay? In other words, what x values do you plug into the parabola and you get y values that are negative? So if we look at the graph, that's happening here. All these points here that go below the x-axis would be the points that you plug in an x value and you get a negative y value. So our solution is to say all the x values that make that happen. So all of these y values down here happen by plugging in these x values right here between negative 4 and 7. So we would say that x would be between, positive 4 and negative 7. And not equal to because the inequality didn't have that. Okay? So the next thing I want to look at, okay, is I want to look at another way to analyze this. So here's a second way to analyze this. The beginning is the same. You identify negative 7 and positive 4 as your zeros and that they can't be exactly equal to them. And you can do it by plugging in numbers. Okay? Basically, I want to know when is this quantity times this quantity less than 0. So plug a number in over here that's smaller than negative 7. So think maybe negative 10. When we plug in negative 10, we would have a negative times a negative, and when those multiplied together, we would end up having a positive. Okay? Now think about plugging a number in between negative 7 and 4. Maybe something like 0. Okay? That would make a negative times a positive, and overall that would make negative. So again, I'm thinking about plugging those numbers in here for x. Okay? Now think about plugging a number that is bigger than 4. When I plug in a number that is bigger than 4, if I plug that into the x minus 4, I would get a positive. If I plug it into the x plus 7, I'll get a positive. And overall, that will be positive. Okay? But remember, I wanted this result, this multiplication problem, to turn out to be less than 0, meaning I want to know where it was negative. Notice it was negative right here. That was the section between -4 and -7. So again, x would be between -7 and 4. Okay. Sorry, I think I keep saying -4 and 7 when I'm saying it fast. All right, so we're going to use that method each time we look at one of these problems. So the next one, if we want to look at positives and negatives, that means we want to be comparing it to 0. So first I would move over the 5, and then I would work on factoring. So once I do that, this is what I'm analyzing. When is this multiplication problem, p minus 5 times p plus 1, less than or equal to 0? Okay. So again, on my x-axis, I know it would exactly equal 0 at -1 and positive 5, because that's what I would get when I set each factor equal to 0. Because it can be equal to, these would be points that would be included. They are part of the solution because they make it equal to 0. Okay? And now I'm going to plug stuff in. So let's think about plugging in a number smaller than -1. If we plug it in here, think like -2. -2 minus 5 would be a negative. -2 plus 1 would be a negative. The negative times the negative makes a positive. Okay? Think about plugging in a number between -1 and 5, like 0. So we plug 0 in here. 0 minus 5 would be a negative. 0 plus 1 would be a positive. Those multiply together to make a negative. Think about plugging in a number bigger than 5. Okay? So 6. 6 minus 5 would make a positive. 6 plus 1 would make a positive. Those multiply together to make a positive. Okay? So my solution, again, is the place where this multiplication problem was less than or equal to 0. So I already marked where it was exactly equal to 0. And then the question is, where is it less than 0? That happened right here where it's negative. So here, p would be less than or equal to 5, and at the same time greater than or equal to -1. Okay. So the analysis here is extremely important that we're using that properly. All right, we're going to go ahead and skip part C, but we're going to look at the try these because they have some special situations. So try these part A. I'm going to call that d squared plus 8d. And then I'm going to add 16 to both sides, again, to get it set equal to 0. So when we factor this, this is a perfect square, okay, which means when we're looking at the number line, there's only one value that's going to make it equal to 0. D plus 4 set equal to 0 only happens when d is equal to -4. Okay? So when d is equal to -4, this will be equal to 0. So it is allowed to equal 0. So I'm going to go ahead and mark that point of -4. Okay. Then the question is, when is it greater than 0? So let's thinking about plugging in our numbers. Plug in something smaller than -4, like -10. That's going to make a negative when you plug -10 in for d. And then you're going to square it, and a negative squared becomes a positive. Think about plugging in something bigger than -4, like 0. 0 plus 4 would make a positive, and then we'd square it, and the end result would be positive. Okay. Our question is, when is d plus 4 squared, this quantity, greater than 0? So in other words, we want to know when it's positive or equal to 0. Well, it was equal to 0 at -4. It was positive here and here, which means all of these numbers smaller than -4, all of these numbers bigger than -4. Notice that I've highlighted the entire number line. So in this case, the solution would be all real numbers. Okay? All right, let's look at part B. Again, it's a perfect square, so we could factor it. And then the only 0, where it's going to exactly equal 0 on the x-axis, or in this case, they're using the letter f, would be at -6. But it cannot be equal to 0. It says only less than 0. So I'm going to make an open point at -6. So when I plug in numbers that are smaller than -6 for f, they're going to make a negative number squared that will then become a positive. And numbers smaller than -6 will make a positive number, larger than -6, like 0 or 1, will make a positive in the parentheses, and when you square it, it will be positive. Okay? I am looking for places where this quantity turns out to be less than 0. In other words, where did this turn out to be negative? Okay? Well, it turned out positive on this side and positive on this side. And it can't even be equal to negative 6 because it's not allowed to be equal to 0. So nothing on my number line is highlighted. So in this case, there is no solution. Okay? All right, so last one we're going to look at is part C. So again, this is a perfect square. Okay. And then this time, if we set 3v minus 1 equal to 0, we would get 1/3 as our solution. Okay? And we can be equal to 0, so that's going to be a filled-in point for that boundary. And then let's think about plugging stuff in. So plug in numbers smaller than 1/3, so like 0. If I plug 0 in for v right here, this quantity is going to become negative, but then it's going to be squared, so the final answer will be positive. If I plug in numbers bigger than 1/3, like 3, for v, this quantity will be positive, and then it will be squared, and it will still be positive. Okay? The question is asking, when will this thing be less than or equal to 0? So I want to know when it's going to be negative or equal 0. So there is no place where it's negative, but the point at 1/3 was filled in because it could equal 0 at that point. So none of the areas to the left or to the right meet the requirement, but the value of 1/3 does meet the requirement. So that one number is a solution to this inequality.